Hi, this is Math372, complex analysis, lecture 23. In honor of 2 and 3 being the sizes of the first non-trivial n by n by n Rubik's cubes, I guess we're starting today with a quick question. How many pieces do you have on a n by n by n cube? So n by n by n cube. So on a 2 by 2 by 2 cube, how many pieces do we have? 8. We have 8 pieces. On a 3 by 3 by 3, how many pieces do we have? Sorry, the video was not recording the beginning. So we're doing the number of pieces on an n by n cube in honor of today being the 23rd lecture and 2 and 3 being the first good sizes. So we have 26 pieces. How should you view the number 26? Not 27 minus 1. How should you write 27?
3 cubed.
And how should you write 1?
1 cubed.
1 cubed. So if I give you an n by n by n cube, how many pieces do you have on an n by n by n cube?
N cubed minus n minus 2 cubed.
Right. Okay. So this is, the reason I was somewhat justified doing this in a complex analysis class is whenever you have a problem, do smaller, simpler cases. Try to build up intuition. And try to think, how should I write the number? This was 26. How should I write 26? I can write this as 26. I can write it as 27 minus 1. But the real good way to write it is 3 cubed minus 1 cubed. And then when you see it like that, then the pattern is clear. Is that if I have an n by n by n, I have an n minus 2 by n minus 2 by n minus 2 inside. And if I remove that, then that's all the pieces that are left over. So nice little exercise. OK, so what we're going to do today is we are going to talk about what we need to get a better analytic continuation of the Riemann zeta function. And we will see that we need a functional equation for what's called a theta function. And this will then require us to do probably about a week's detour into Fourier analysis. And so I will try to prove all the big theorems, or at least some of the big theorems in Fourier analysis in a week. There's a small aside in the book where they say, and now we need a result from an earlier book in the series. It's a result that's of interest in its own right. We can actually use it to calculate a lot of things we really care about. For instance, the sum of 1 over n squared is pi squared over 6. How many of you have seen a proof of that? Good. We'll be able to get a proof of that from the stuff we're doing. So even though this may seem like a little bit of a detour, it's going to actually help us resolve a lot of things that have come up before. The other thing is, as I've said, I want to slow down the pace right now for the last part of the course. I want to do advanced topics. Basically, the only way they will occur on the final exam is I will say, here's a bunch of topics we looked at the end of the semester. Choose one, do a problem related to it, or write about it, something like that. There'll be a lot of freedom. I want you to see where mathematics goes. This is a graduate level class. Because I am a number theorist, not surprisingly, a lot of the applications and a lot of where does this go, it goes to number theory. Partly because a lot of this was motivated by people trying to do number theory. All right, so towards the functional equation of zeta of s. So we've already shown how to analytically extend this using the alternating series. This is a really good, cheap continuation, but we saw it doesn't go far enough for what we need. So we need a little bit more. So what we're going to do today is we're going to set up the stage for the real continuation. And so we're going to use the gamma function. So gamma of s is equal to the integral from 0 to infinity of e to the negative x, x to the s minus 1 dx. And we talked about how this integral makes sense as long as the real part of s is greater than 0. We showed that it has a continuation. Gamma of s plus 1 is s gamma of s. You can figure out where all the poles are, what all the residues are. The function 1 over gamma of s is very nice. We will need the function gamma of s halves. Being at the well, since not everybody's at the blackboard, I'll just write it again. It's really not that hard to do a search and replace and just put an s halves where all of those are. Okay. And the quantity we want to look at, it's off to the side, so I can actually try to pretend I'm memorizing all this stuff and giving the good lecture. 85% chance I would have gotten it right anyway, but why not use the sideboard? And so I want to look at pi to the minus s halves, gamma of s halves, n to the minus s. And the claim is that this is equal to the integral from 0 to infinity of e to the negative pi n squared u to the s halves minus 1 du. Okay? So when we look at this, does this seem reasonable? That something like this, I may have an algebra mistake. It's late enough in the semester that you should expect an algebra mistake. But does something like this look plausible? If you look at the gamma function, well, instead of having an e to the minus x, I now have like a minus pi n squared. So I'm going to have to do a change of variables. If I put that in here, I'm going to have some stuff coming out here. I'll then pull that out. That's going to have things to the s. Something like this looks reasonable. Yeah, it's got pi's coming in. It's got n's coming in. So let's now try to prove this. So proof. So we start off with gamma of s halves. There's probably lots of different ways of doing this. Is equal to the integral from 0 to infinity e to the negative x, x to the s over 2 minus 1 dx. Let's let x equal pi n squared u. That seems the most natural thing to do because I want to get an e to the minus pi n squared u. Let's take that. Dx becomes pi n squared du. And now we'll get gamma of s halves is just the integral. Well, the range of integration is not going to change. It would be 0 to infinity. E to the negative pi n squared u. Now over here, I'll have a pi n squared u to the s halves minus 1 du. Well, the u to the s halves minus 1 is exactly what I want. And then I have a pi n squared to the s halves minus 1. I now need to just bring this over to the other side. Except dx is not just du, it's pi n squared du. I knew there would be an algebra mistake somewhere. This extra pi n squared u cancels the negative 1 over here for the pi n squared. And so I just have pi n squared to the s halves. So when I bring it all over, I now have pi to the negative s halves, gamma of s halves, and then I'll have an n squared to the s halves. That's an n to the s, comes over on the other side as an n to the minus s, is equal to the integral from 0 to infinity, e to the negative pi n squared u to the s halves minus 1 du. Did I lose something? No, that's canceling the. OK. All right, so that proves the first claim. What should we do to both sides of this equality now? Now that we have this, what should we do? So this is no longer a claim. We now have this relation. So pi to the minus s halves, gamma s halves n to the minus s equals this integral. What function am I trying to get? What function do I want to emerge? I want the Riemann zeta function. All right? Zeta of s is the sum, and goes from 1 to infinity, of n to the minus s. So when you look at this, this almost has the zeta function, right? All we need to do is sum over n. Now, when we sum over n here, notice that this part of the integrand doesn't depend on n. All that depends on n is this part here. So do you think we can interchange the integral and the sum? If we couldn't, I probably wouldn't be doing this approach, right? So based on the fact that this is being done in a class, almost surely we can justify interchanging the integral and the sum. This has incredibly rapid decay. So e to the minus pi u already has exponential decay. As n gets larger and larger and larger, it's going to get smaller and smaller and smaller. So now we sum over n. And when we sum over n, we get pi to the minus s halves, gamma of s halves, zeta of s, is equal to the integral from 0 to infinity, the sum, n goes from 1 to infinity, e to the minus pi n squared u to the s halves minus 1 du. And the way you can justify something like this is if the integral of the absolute value is finite, then you can justify the interchange. How can we estimate this? How bad could that sum be? So we need some small control. So we have the sum n goes from 1 to infinity e to the negative pi n squared u. Can you think of anything that would dominate that might be easy to work with? Okay, so good. What geometric series do we want? When in doubt, we always go back to the geometric series. It's our go-to sum. So what geometric series is this very close to? Well, can you give me a geometric series that term by term dominates? E to the negative pi u, e to the negative pi 2 squared u, e to the negative pi 3 cubed, 3 squared u. Yeah, just drop the square. If you drop the square, it's going to be less equal to the sum n goes from 1 to infinity e to negative pi n u. This will be less than equal to e to negative pi n u over 1 minus, e to negative pi u over 1 minus e to the negative pi u. So what do you think?
Why do you have the negative pi u on top, or even negative pi on top?
Well, because the sum is starting at 1, not at 0. So because it's starting at 1, we have an e to the negative pi u. So what do you think? Is this a good bound?
As long as e to the negative pi u isn't negative 1, should be good.
Well, u is a real variable. U is going from 0 to infinity. So as long as u has anything that's positive, this is going to have great decay. The only trouble is near u equals 0. And so near u equals 0, the question is, how bad is this? Because this is going to be exploding, unfortunately. As u goes to 0, we have e to the negative 0, which is 1. So what would be the size of something like this as u gets very, very small? This is going to go off to infinity. So the question is, how badly will it go off to infinity?
Like 1 over x, or 1 over u.
It's going to look like 1 over u up to a constant. Because if you look at this, 1 minus e to the negative pi u, this is 1 minus 1 minus pi u plus pi squared u squared over 2 factorial. So this is going to be pi u minus pi squared u squared over 2 factorial. We factor out the pi u, we get pi u 1 minus pi u over 2 plus dot dot dot. So this is going to look like a 1 over u. So as u goes to 0, looks like 1 over u. Unfortunately, 1 over u blows up. But if we look at what we have over here, we have a u to the s halves minus 1. So as long as that is a positive number, it's going to be integrable. So we have the extra fact of u to the s halves minus 1. So we're OK if the real part of s halves minus 1 is greater than 0. Then we will have something that's integrable. If you want to be really safe, make it greater than 1. And then if it's greater than 1, now you'll have a nice continuous function. So this is one of the reasons why when we look at the Riemann zeta function, we often start off in a region where things converge really well. We'll start off maybe with the real part of s greater than 2. And if we start off with the real part of s greater than 2, we should be fine. So actually, we would want a little bit more than that here. That would be more like real part of s greater than 4. Okay? So we just have to be slightly careful whenever we do, analysis like this. Can we justify the interchange? It's clear that we want to do the interchange. We'd love to evaluate a sum like this. But the problem is if every value of u is 0, then we have a problem. Okay. Any questions about this argument?
Why do you need s halves over 1 greater than 4?
Well, just because this part is looking like 1 over u.
Yeah.
If I multiply this by something that's at least a u to the 1 plus epsilon, then I'll have something that will look like u to the epsilon, and it'll be a nice continuous function. And so I would need s halves minus 1 to be greater than 1. So I would need s halves to be greater than 2. So I would need s to be greater than 4. So if the real part of s is greater than 4. Yep, exactly. So we would probably want this maybe to be greater than 2, I think. Or did I want that to be greater than 1? No, sorry. If that thing is greater than 1, then that implies, your real part of s greater than 4. And the Riemann zeta function converges so nicely, it's okay if you've moved a little bit further to the right than you need to. But we do have to be careful, because if we take u equals 0 at every single point, it does blow up. And an analysis like this is not valid.
Wait, actually, no, I stopped doing it.
So,
I like this makes you don't want.
So if this part is looking like 1 over u, if this part here looks like u to the 1 plus epsilon, then this whole thing is still going to be continuous. Okay. So how can I get this to look like u to the 1 plus epsilon? I need s halves minus 1 to equal 1 plus epsilon. So I need s halves to equal 2 plus epsilon. So I basically need s to be a little bit greater than. Okay. Let's do an aside. Let's look at a calculation similar to this, and need to be careful. I'll save this because we will need that again in a moment. It involves pi's, it involves integrals, it involves functions we've seen before. So this is not a bad thing. This is the Gregory-Leibnitz formula. So how many of you have seen the Gregory-Leibnitz formula? Or if you've seen it, you do not remember that it is the Gregory-Leibnitz formula. All right, so let me see. There's a couple of ways to do it. Let's integrate from 0 to 1 dx over 1 plus x squared. What function has derivative 1 over 1 plus x squared? Inverse tangent or arctangent, as a Bostonian likes to say arc. So we have arctangent of 1 minus arctangent of 0. What angle has a tangent of 1? That's 45 degrees or pi-fourths radians. We always work in radians. What angle has a tangent of 0? That's just 0. So this is just pi over 4. So this integral is pi over 4. So one way to calculate pi over 4 is to just calculate this integral really, really well. Okay? When you look at this integral, what do you see? I feel like I'm giving you like a Rorschach test. Yeah, it looks a lot like a geometric series. This is equal to the integral from 0 to infinity, 1 over 1 minus negative x squared dx. This is equal to the integral from 0 to 1. The sum then goes from 0 to infinity of negative x squared to the n dx. This is the sum, and goes from 0 to infinity, negative 1 to the n, integral from 0 to 1 of x to the 2n dx. This is the sum, and goes from 0 to infinity, of negative 1 to the n. I get x to the 2n plus 1 over 2n plus 1. I'm evaluating it at 1 and 0, so I just divide, I get 1 over 2n plus 1. So you get 1 minus a third plus a fifth minus a seventh equals pi over 4. You can write this as an infinite product. Anybody want to guess what infinite product that would be? I think this would just be the product p is a prime greater than 2, 1 minus, what do you think? I think 1 plus 1 over p inverse. So when I expand this out, oh wait a minute, is this going to be right? No, this is not going to be right. No, I don't want to go down that route right now. I'm gonna leave it like this. I'm gonna make an algebra mistake. I'm gonna stop. I will resist to going too far off. But this gives you pi over 4. This gives you an alternating sum formula for pi over 4. It looks a lot like the zeta function, except now we have pluses and minuses. And it basically just depends on are you an odd number, and are you 1 mod 4 or are you 3 mod 4? So the product it would be the sum of 1 minus chi of p over p to the minus 1, where chi of p is 0 if p is 2, it's 1 if p is 1 mod 4, and it's negative 1 if p is 3 mod 4. And then if there was only finitely many primes, it would be a finite product. It would be rational. Pi is irrational, therefore there must be infinitely many primes. So this is another proof of the infinitude of primes. I can't help prove it. Almost anything you try seems to give a proof of the infinitude of primes. Do you like this proof, or does this proof give you any pause? The result is correct, but is the algebra justifying it correct? What do you think? Are there any places where you're a little worried?
The interchange of the integral and sum.
Yeah, I mean, when in doubt, whenever you interchange an integral and a sum, you should be worried. There's actually a place to be worried a little bit before then.
Oh, with using the geometric series formula?
Yes. Why might it be dangerous to use the geometric series formula?
Because it's only applicable when the negative x squared is between has absolute value less than 1.
Right. And so if you look at this, when x equals 1, we have negative 1 to the n. So we have an alternating sum, negative 1, 1, negative 1, 1, negative 1, 1, negative 1. Now, if you have this alternating sum, negative 1, 1, negative 1, 1, and you add them all, what should that equal? And I think we actually start at 1. So it's 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. So what should 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 be if we do that infinitely often? So half the time, if we stop at an odd place, it's 1. Half the time, we stop at an even place, it's 0. So in the interest of harmony, what should we call it? A half. And if you put in x equals 1, what do you get? You get a half. This can all be justified. What you really need to do is you replace this 1 with an epsilon. And then you take the limit, as 1 minus epsilon, as epsilon goes to 0. And then you would have, over here, a limit as epsilon goes to 0. And then here, you would have 1 minus epsilon to the n. And you would take a limit as epsilon goes to 0. And then everything will be fine. This limit does exist as epsilon goes to 0. So you can make this rigorous. So a lot of times, you want to do these fast, quick calculations. And then you spend some time going through and making the analysis rigorous. This is similar to what we had with this function over here. We had to be just a little careful at one place. Otherwise, everything is fine. And so I thought, based on how things were going, it was not a bad idea to just do a brief digression, look at the Gregory-Leibnitz formula, get a formula for pi over 4, prove again the infinitude of primes, and just see the difficulties with the interchange, see the difficulties with how you do these estimations. Okay, so now just rewinding in time, we now come back to this expression over here. So we have a formula for zeta of s times gamma of s halves times pi to the minus s halves. And because this occurs so often, we call this the completed zeta function. And we often denote it as c of s. And the big theorem is it turns out that this is also equal to c of 1 minus s. And this is what's going to furnish the analytic continuation. So it all comes down from looking at this expression over here. And so now we're getting to the point where we will see why we need to do complex analysis and Fourier analysis. So we have this expression, the sum of e to the negative pi n squared u. As long as u is not 0, this has really nice decay. And so what we're going to do is define a theta function. As I'm going to define theta of u minus 1 over 2 is the sum, n goes from 1 to infinity, e to the negative pi n squared u. And another way of seeing this is if I move the 2 over here, because I have n squared, this is the same as n goes from negative infinity to infinity, except I exclude 0. Well, if I take n equals 0, I get 1. So if I move this 1 over to the other side, what you're really seeing is I'm really defining theta of u to be the sum, n goes from minus infinity to infinity, of e to the negative pi n squared u. The n equals 0 term is just that 1, and the 2 is because the evens and the odds contribute the same. This function has a remarkable property. Anybody want to guess what that remarkable property is? The glories of the sideboard, right? It equals u to the negative 1/2 theta of 1 over u. So it allows you to take its values at one place and get its values at another place. And it's this transformation property over here that's going to lead to the functional equation of the Riemann zeta function. So what we will have is we will have c of s is equal to the integral from 0 to infinity. Now what we have over there, we have the sum n goes from 1 to infinity, e to the negative pi n squared over u. All right, so this is going to be theta of u minus 1 over 2, u to the s halves minus 1 du. And then what we'll do is we're going to break this integral 0 infinity into an integral from 0 to 1 and an integral from 1 to infinity. And then in the integral from 0 to 1, we can use this and convert it to an integral from 1 to infinity and combine things. So I will leave you to read the book now to just finish the algebra of how you would now just play the games, use the transformation property to split the integral up into two pieces, collect all the stuff, find your mistake, do the argument again, and when the dust settles, you will get a nice continuation of the Riemann zeta function, and you'll express it as a convergent integral. So we've basically reduced all the work to the following remarkable formula. The question is, why is this true? Frequently in mathematics, the way you prove something is true is you prove a wider class of things holds, and then this is just a special case. And so what we're going to do is we're going to lead up to what's called Poisson summation. It's one of the most powerful techniques we have in mathematics to evaluate sums. So how many of you have seen Poisson summation before? Okay, good. So we're going to get some real dividends for the stuff we're doing in complex analysis. And so this is a first course. This is an introduction. I am not going to prove the results in the greatest possible generality. I will prove the results in enough generality for all the cases we care about. So Poisson summation. If f is nice and f hat is its Fourier transform, and that's f hat of y is the integral from minus infinity to infinity of f of x e to the negative 2 pi I xy dx. Then the sum, n goes from minus infinity to infinity of f of n, is the same as the sum, n goes from minus infinity to infinity of f hat of n. Question? Or? Okay. So I've at least defined what the Fourier transform is. This clearly looks like an object that deserves to be studied in a complex analysis class. You know, if you see an I, it's justified. When I'm going off and I'm proving yet again that there's infinitely many primes because pi is irrational, pi squared is irrational, you have a right to be a little bit concerned that you're getting the right class. But once you see an I, it's absolutely fair game. Now, what word do you think I need to define? Nice, yeah. So that's where the real meat is. What functions will satisfy this? It turns out the theta function is nice enough. There's a good enough decay that everything is well behaved. Now, we want to be able to compute Fourier transforms. We've actually been computing Fourier transforms throughout the semester. We haven't explicitly said this, but a lot of times we've been doing these contour integrals, and we've had factors like that. The thing that's a little bit different is which letters do you use? We would not typically use letters x and y in our complex analysis book because we write z as x plus iy. So we might be using a and b or something like that. People often use c as the variable for Fourier transform, but given that we're using c for the completed Riemann zeta function, I would prefer not to use that letter. It turns out that the Fourier transform of the Gaussian is another Gaussian. And so what's really going on there, the e to the negative pi n squared u is very, very nice. It just changes basically the variance. So we'll look at that calculation later, but the stuff we were doing earlier on how do you find the Fourier transform of the Gaussian, how to do these integrals, is going to now play huge dividends here. Okay? So this is the formula we're leading up to. And this will get us the theta function. So the question is, how do we get there? So it's what is the fastest proof to Poisson summation, which along the way will lead to nice results that will be of interest. So how many of you have taken a physics class where you've used sines and cosines to approximate functions, you know, Fourier series? Okay. So if you've never seen Fourier series, this is something you should see. And then generalizations of this is where wavelets come into play. So Fourier series. And it's very easy to just write things down and hope they converge and then learn later that they don't. But if things are nice, things converge. What do you think nice might mean? If I want a function to be nice, what property should the function have? Yeah, at the very least, the function should be continuous. If the function is not continuous, I'm hesitant. All right, what else? Maybe meromorphic, so maybe differentiable, or maybe only finitely many bad places. Maybe the function should have good decay, so that things converge and I can justify interchanges. You know, you want to have some idea of what kind of properties might you want. So you've seen Taylor series. So for Taylor series, you write things in terms of powers of x. Fourier series, we do things in terms of e n of x. And here, e n of x is e to the 2 pi I n x. Unfortunately, there are at least 3 different ways of normalizing things. You can have a positive sign in some places, a negative sign in some places. You can have a 2 pi. You cannot have a 2 pi. You could have a 1 over square root of 2 pi because you don't want to offend anybody. So you kind of give half to each camp. I think that's the worst. Choose a camp, be in it. Don't try to accommodate everybody. The difficulty is if you look at different books, they will have different notation. And it can be hard to follow. The worst notation I've ever seen was from a physics textbook. Anybody know what equation this is? Yes, this is force equals mass times acceleration, where F was acceleration and P was force. And I'm thinking, P should be momentum, maybe F is frequency, and eventually oh my God, this is Newton's. You want good notation, but worst case, you want to at least know what notation someone is using. I was at Ohio State, and a graduate student, I don't know if I told you the story, when he showed me his thesis, I looked at it and said, wow, this looks really nice. You do realize half your thesis is wrong. And I was having a little fun with the graduate student by phrasing it like this. The look on his face was priceless. And so he was using a paper which assumed that k was even and k was congruent to 0 mod 4. And half of the time, he had k was congruent to 2 mod 4. All this really means is he just has to put in a factor of -1. It was not that bad to fix his thesis. But the point was he was using a paper, and he didn't realize that earlier in the paper, the author said, henceforth, we will always assume k is 0 mod 4. If k is 2 mod 4, you just have to modify the results by putting in a negative sign. You always want to be careful when you're reading things. Now, if you look at this, e to the nx is e to the 2 pi I nx. This is cosine 2 pi nx plus I sine 2 pi nx. And so if we look at e to the nx minus e to the negative nx over 2, this will become cosine of 2 pi nx. So rather than looking at these exponentials, I could do everything in terms of sines and cosines. It wouldn't really matter. I have the 2 pi here, so my x is going to always range from 0 to 1. If I didn't have the 2 pi's, my x would range from 0 to 2 pi. And the idea is I want to express a nice function as a linear combination of these functions here. So now we get to review some linear algebra. So with linear algebra, you want to have 2 things about your basis. The terms should be linearly independent. If they're not linearly independent, you really shouldn't have them. Throw some of them away. And they should be complete. You should make sure you have every direction. So the question is, which functions can be expressed as linear combinations of sines and cosines? And so what we'll do is we will assume f is periodic on 0, 1. And so if it's periodic on 0, 1, then it makes sense that we can start talking about something like this. If your function is not periodic, there's a trick you can do to make it periodic. Let's say here's your function. And I'll just rescale things so it's now on 0, 1/2. So here's my function. This is clearly not periodic. Anybody know how I can make it periodic in 0, 1? Yeah, just reflect it. And so if you then reflect your function, you can start off with a function that's not periodic and now make it periodic and then do the Fourier analysis on it. And then just look at what's going on from 0 to 1/2. So the periodic assumption is actually not that bad of an assumption. So we're going to define the Fourier coefficients. So f hat of n is the integral from 0 to 1 of f of x e to the negative 2 pi I n x dx. Okay? So notice we have a negative sign here. If you think of dot products, have you seen this notation in real analysis? I'm taking the dot product of f with the function en. And the way we define things is you have to take the complex conjugate of the second one because these are complex valued entries. That's where the minus sign comes from. A little bit of a calculation shows that en, em is delta nm. So this is 1 if n equals m, 0 otherwise. This is called the Chronicle delta symbol. My freshman textbook explicitly remarked, note, Chronicle had much greater contributions to mathematics than this. It's a good symbol, though. It allows you to quickly and compactly encode information. And if you just go through this, if I have e to the 2 pi I nx times e to the negative 2 pi I mx, if n and m equal the same thing, then I'm just integrating 1. If they're not, then I have cosine and sine of something that's non-zero, so it's going to oscillate out to 0. So these functions are orthogonal. And in fact, they're more than orthogonal. When I take the dot product with each other, I get 1, so they're actually orthonormal. Each one of these functions has unit length. Have you all seen why we use integration for dot products? Was that justified to you in real analysis? Okay. So, again, I do not have a specific agenda in terms of what I cover. If there are things that you haven't seen in real analysis, this is my chance to either explain them and motivate them or, remedy a deficiency. So the real question is why we define. So you've seen dot products like this in real analysis, but they just haven't motivated why they do this as the dot product. They say, let's call this the dot product. Okay. So I want to motivate why we use this as the dot product, and then I'll end with maybe what the Fourier series is. So let's say I have a function f. I can associate to f the following vector: f of 0 over n, f of 1 over n, dot, 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 f of n minus 1 over n. So I have a nice vector like this. So if I have two functions, f and g, I can say, well, look, I can now view these as vectors. So f dot g, or fg, should now be the sum, n goes from 0 to n minus 1, of f of n over n, g of n over n, bar. And now I'm just taking the dot product of two functions. And now, what limit should I take? So I could take n goes to infinity. The problem is if I take n goes to infinity, what do you think is going to typically happen to the sum? It diverges. Let's take the dot product of 1 with itself, the function that's identically 1. Then I'm going to get the sum, n goes from 0 to n minus 1 of 1 times the complex conjugate of 1. And what will that be? It'll be n. So this actually suggests how we should fix things. Right? What should the dot product of the function 1 on the interval 0, 1 with itself be? It should be 1. So let's put in a factor of 1 over n. And if I put in a factor of 1 over n, now the dot product of 1 with itself equals 1. Good. And what does this look like now?
Just Riemann sums.
It's Riemann sums. And now the real reason for this part of the lecture comes into play. Point for Riemann. Right? We got to mention Riemann's name. Okay? Cauchy was just, cleaning up at the start of the semester. Here's a chance for Riemann to get back in the game. This is a Riemann sum. And this is where the integration comes from. This is why we use this as the dot product. Okay, so now that we have this, what we'll do is we will define the Dirichlet series of order n for the function f at the point x should just be the sum, n goes from minus n to n, of f hat of n, e n of x. So what we're basically saying is, look, take your function f, see how much you have in the direction of en. They're all perpendicular, they're all unit length. And then just take that as the approximation. And so this is a really good approximation, hopefully, to our function. And then all we need to do is what? To recover f, what should we do? Or what would we hope would recover f? Now that we have this, how do you think we would recover the function f? What do you think this should be close to? I'm taking the amount f has in each of these directions, and I'm putting them all together. What should this be approximating? F, right? As n goes to infinity, we hope Sn of f goes to f. And if that's the case, that means that these directions are complete, that it covers the entire space. Now, because there's infinitely many directions, it is going to be a real challenge. It is not the case that this will always recover the function f. It will recover the f at certain places. But there are some functions which are integrable, which unfortunately the Fourier series converges almost nowhere, I think, to the function. So convergence is extremely delicate, unless you make your function nice. And if you make your function really nice, then the convergence is trivial. The other thing is this allows me to talk about discrimination again in a good way. We decided that it was okay to discriminate a small amount among primes, right? Not a huge amount, but a small amount of discrimination is okay. It turns out a small amount of discrimination on the Fourier coefficients is fine. We will, in Wednesday's lecture, look at the Fourier series. So the Fourier series of f at x is the sum, n goes from minus n to n, of 1 minus the absolute value of n over n, f hat of n, en of x. And this goes back to a comment I made briefly a while ago, that sharp cutoffs are bad in mathematics. That if you all of a sudden say, stop, it's very hard analytically to work with that. But if you have a nice gradual cutoff. Now, there are situations in the real world where you cannot do this. We cannot admit 93% of somebody to Williams College. Right? But here, notice what happens. When little n is small, let's say the absolute value of n is less than the square root of n. When it's less than the square root of n, this is insignificant. And you essentially get the full coefficient. Conversely, if the absolute value of n is greater than n minus the square root of n, then this is basically the size 1 over square root of n, and it's insignificant. So that there are ranges where the contribution is strong and weak. This has remarkably nice convergence properties. All we need is that the function f is continuous, and we can show that this will converge to the function. If the function is differentiable, then the Fourier series will converge to the function at the point. In fact, you don't quite need differentiable. How many of you have seen Holder conditions? So if you've seen Holder conditions, something like that will suffice. So I will see if I can actually pivot far enough. OK, so it looks like I can actually pivot far enough. So for the next class, we'll look at these two functions, the Dirichlet kernel and the Fourier kernel. So the Dirichlet kernel is the sum n goes from negative n to n of en of x. And the Fourier kernel is basically a weighted sum of Dirichlet kernels. It turns out that the Dirichlet kernel has a nice closed form expression, as does the Fourier kernel. How do you think we evaluate this Dirichlet sum? How do you think we got that at the end? What do you think we used? How do you think we evaluated this sum? Does this sum look like anything you've seen? So it's the sum, n goes from minus n to n, of e to the 2 pi I nx. This sum has a name. What kind of sum is this? There's not that many sums we know. What kind of sum do you think it might be? Geometric. So we would have to have something to the nth power. Oh yeah. This is just the sum n goes from minus n to n of e to the 2 pi I x to the n. That's our r. So the way you would calculate the first part is you would just use the geometric series formula and then just do some algebra. And then you do algebra on algebra for the second. So I'll leave those as exercises for you to think about, and then we will continue with Fourier analysis on Wednesday.